Hi students, in this session, I'm going to explain you some basic topics with respect to jet transforms. Okay, so to understand the concepts of jet transforms, we have to know these basic things. Why? Because jet transform is completely with respect to discrete time signals. Discrete time signals. Up to now, we discussed about continuous time signals because already you've seen the Laplace transform. So we use this Laplace transform for continuous time signals. Whereas if we have the discrete time signals, we have to go for jet transforms. That is, these jet transforms are mainly for discrete time signals. Okay. So for that reason, we have to differentiate the continuous time signal and discrete time signal. First, I go for the fundamental difference between continuous time and discrete time signals. Already I explained you clearly what is a continuous time signal and what is a discrete time signal. What are the differences? So continuous time signal is generally represented with x of t and discrete time signal is generally represented with x of n. So I am going for the fundamental difference between these two. Because why? Because I already explained you what is a continuous time signal and what is a discrete time signal. You know everything about that. So I am going for the differences. Continuous time signal is represented with x of t. Discrete time signal is represented with x of n. And the continuous time signal, we have a continuous waveform like this. And in the discrete, we have the amplitude for only discrete instants of time. We have only the discrete, that is n, x of n, t, x of t. See here for all instants of time we have the signal, and here we have the signal only for discrete instants of time. Okay, as this is discrete. Okay, just I'm again reviewing what I explained in this. I'm briefing the fundamental difference between continuous time signal and discrete time signal. If you go for the exponential, that is real exponential with respect to continuous time and with respect to discrete time also. So I already explained you. So with respect to continuous time, the real exponential, either decaying exponential or increasing exponential. This is for continuous time real exponential. In the same way, discrete time real exponential will also decaying, we have the decaying ones and we have the increasing ones. Okay, so this is for continuous time real exponential and this is for discrete time waveforms. Just I shown the waveforms. Already I have given the equations and all the figures. Just these are the basic differences. Okay, here the continuous time signal exists for all instants of time, whereas a discrete time signal exists only at discrete instants of time. So these are the signal diagrammatic representation of continuous time and discrete time, and this is the continuous time real exponential signal and this is the discrete time real exponential signal. Okay, clear? Now next, the important one is discrete time signal representation using complex exponential and sinusoidal components. Discrete time signal representation. So you have to represent the discrete time signal. Why? Because I said jet transform is completely with respect to discrete time. So I have to know how the discrete time signal is represented using complex exponential and sinusoidal components. So sinusoidal, that is either sine or cos. Complex exponential, that is e power j omega. So in these two, how we have to represent the discrete time signal. Okay. Now first I will go with continuous time, then I will go to the discrete time. See, the complex exponential, first the continuous time signal x of t, the complex exponential continuous time signal will be known as e power j omega t, whereas for discrete it is e power j omega naught n. Continuous, it is e power j omega naught t. So you can write j omega naught t or j omega naught t, whatever it may be. So e power j omega t continuous. In place of t, if you write n, then it will be discrete. For discrete, x of n equal to e power j omega naught n. In the same way, sinusoidal signals. For continuous, you can write as x of t equal to cos of omega t plus phi. Whereas for discrete, we can write as x of n equal to cos of omega naught n plus phi. Now, this complex exponentials in terms of sinusoidals. Complex exponentials in terms of sinusoidals. You have Euler's formula, e power j theta equal to cos theta plus j sin theta. By that, I can write e power j omega naught t equal to cos omega naught t plus j sin omega naught t. For continuous time signal, for discrete time signal, e power j omega n will be equal to cos omega naught n plus j sin omega naught n. So with this I can represent a complex exponential discrete time signal in terms of the sinusoidal signal components. Okay, discrete sinusoid. Next, I can represent the sinusoidal components in terms of complex exponentials also. Reverse one, that is cos of omega naught t plus phi will be equal to e power j of omega naught t plus phi plus e power minus j of omega naught t plus phi by 2. Simply cos theta will be equal to e power j theta plus e power minus j theta by 2. Cos theta equal to e power j theta plus e power minus j theta by 2. Using that formula, I can convert the sinusoidal into complex exponentials also. This is for continuous time. This is for continuous time. And for discrete, I have to replace t with n. So cos of omega naught n plus phi will be equal to e power j into omega naught n plus phi plus e power minus j. E power minus j into omega naught n plus phi by 2. So this is the how the discrete time signal representation using complex exponential and sinusoidal components. Along with the discrete, I had shown you the continuous time also, because already you know the continuous time. By using this, I shown you the discrete time signal representation using complex exponential and sinusoidal components. Okay, so this is your second topic. And next one, we move on to the periodicity of this discrete time complex exponentials. Discrete time complex exponentials. Periodicity. So we have to go for the periodicity. Find the what is meant by periodicity. When we say a signal is to be periodic, either it is continuous or discrete. So we are going with respect to discrete. First I will explain what is the periodicity with respect to continuous time signals. You all know, when we say continuous time signal is periodic, if x of t equal to, if x of small t equal to x of small t plus capital T, then I can say the continuous time signal is periodic. When we say a discrete time signal is periodic, in the same way, if x of small n will be equal to x of small n plus capital N, then I can say the discrete time signal is periodic. So this is the condition for periodicity. So for periodicity, it has to satisfy the condition x of small n will be equal to x of small n plus capital N. The same, x of small n will be equal to x of small n plus capital N. So if it satisfies this condition, then I can say it is a periodic signal. So now I have to go for the periodicity of discrete time complex exponential signals. So for any signal, if I want to say if it is a complex exponential, if I want to say it is a periodic, it has to satisfy the condition x of n equal to x of small n plus capital N. First, the discrete time complex exponential is represented with x of n equal to e power j omega naught n. We already see that. So x of n equal to e power j omega naught n. Next, for periodicity, it has to be equal to x of small n plus capital N. Hence, I got the equation for x of n plus capital N, small n plus capital N equal to e power j omega naught into n plus small n plus capital N. Simple. So first I know I have the x of n. So then from that I gone for the equation of x of small n plus capital N, that will be equal to e power j omega naught into, in place of n I have to substitute small n plus capital N, that will be equal to e power a plus b, e power a into e power b. In the same way, e power j omega naught n into e power j omega naught capital N. Okay. Now according to the periodicity, x of n should be equal to x of small n plus capital N. That means these two will be equal. So for periodicity I have to equal e power j omega naught n will be equal to e power j omega naught n into e power j omega naught capital N. Okay. Now e power j omega naught small n and e power j omega naught small n will be gets cancelled. These two cancel. So e power j omega naught capital N will be equal to 1. E power j omega naught capital N will be equal to 1. But you know the formula for this one. E power j omega naught small n, I have the formula. In place of small n, I have the capital N here. So what is the formula for e power j omega naught capital N? That will be equal to cos of omega naught capital N plus j into sine of omega naught capital N by Euler's formula. E power j theta equal to cos theta plus j sin theta. Already I had given this here. So I have gone for this one. Now for periodicity, e power j omega naught n should be equal to 1. Already I know the value of e power j omega naught n as cos omega naught n plus j sin omega naught n. That is for periodicity, cos omega naught n plus j sin omega naught n will be equal to 1. For periodicity, cos omega naught n. Period. This n is period. This capital N. is period. Cos omega naught n plus j sin omega naught n will be equal to 1. Okay, the above equation is true, or the above equation will be satisfied for the values of omega naught n. Omega naught n will be equal to 2 pi, 4 pi, 6 pi. That is cos 2 pi plus j sin 2 pi. So this is 0 and this is 1. Cos 4 pi plus j sin 4 pi. This is 0 and this is 1. It is 1. So this equation will be satisfied for the values of omega naught n equal to 2 pi, 4 pi, 6 pi, 8 pi and so on. That is, this equation is true only when omega naught n will be equal to 2 pi, 4 pi, 6 pi and so on. Okay. Now that means I can write this 2 pi, 4 pi, 6 pi so on as 2 pi k. 2 pi k where k is an integer. If k equal to 1, 2 pi, k equal to 2, 4 pi, k equal to 3, 6 pi, k equal to 4, 8 pi, 8 pi, k equal to 5, 10 pi, so on. So I can represent this as 2 pi k. Okay. Now we get omega naught n will be equal to 2 pi k where k is an integer. K is an integer. So from this I need the value of omega naught by 2 pi. So bring this side and bring this side. So what happens? Omega naught by 2 pi equal to k by n. Omega naught by 2 pi equal to k by n. This is the condition for discrete time complex exponential to be periodic. So if you want to say discrete time complex exponential signal to be periodic, then it has satisfied omega naught by 2 pi will be equal to k by n, where k is the integer. K is an integer and n is the period. Okay, is the period. Simply that is also an integer. Okay, hence omega naught by 2 pi will be a rational number. Simple. And we know the value of omega naught. Omega naught equal to 2 pi f. 2 pi f. So 2 pi f divided by 2 pi equal to k by n. 2 pi cancel. Is f equal to k by n. Or simply the frequency is a rational number. Then I can say that discrete time complex exponential signal is a periodic. Rational number is nothing but ratio of two integers. Here f equal to k by n. K is an integer and n is a period. If f value will equal to k by n, then I can say this is a periodic. That discrete time complex exponential is a periodic. Or if you want to say discrete time complex exponential signal to be periodic, it has satisfied the condition omega naught by 2 pi will be equal to k by n, where k is the integer and n is the period. Simply k and n both are integers, then it will be a rational number. That is omega naught by 2 pi, and must should be a rational number. It will ratio of two integers like k by n, where k is an integer and n is a period. Clear? So this is the periodicity of discrete time complex exponential signal. There is a condition. It has to satisfy to be period. That is, discrete time complex exponential is said to be periodic. It has to satisfy the condition omega naught by 2 pi equal to k by n. So in this class, the basics, account for the basics, that is continuous time signal and discrete time signal. Continuous time real exponential signal and discrete time real exponential signal waveforms. Because already I had given the complete lecture videos of this continuous time and discrete time. So I already explained you clearly of this continuous and discrete time signals and a real time continuous time exponential signal and a real discrete time exponential. Okay, continuous time real exponential signals and a discrete time real exponential signals also I already explained you with all the waveforms. Okay, so the next topic I explained is discrete time signal representation using complex exponential and sinusoidal components. How a discrete time signal is represented with complex exponentials and sinusoidal components. I explained you. So first I gone with continuous time and then I went to discrete time for your easy understanding. And next topic is periodicity of discrete time complex exponential signals. Then I gone for the periodicity of discrete time complex exponential signal. You know the condition for periodicity. That is, for continuous time it is x of small t equal to x of small t plus capital T, whereas for discrete time it is small of x of small n equal to x of small n plus capital N. And I have the equation of complex exponential x of n. From that I account for x of small n plus capital N, and I equated those two for getting the condition for periodicity, and I simplified and I used the Euler formula for this one, and I got this one as this. So here, if this equation has to be satisfied, the values of omega naught n will be equal to 2 pi k, where k is an integer, and from this I can get omega naught by 2 pi equal to k by n. So this is the condition. Omega naught by 2 pi equal to k by n is a condition for discrete time complex exponential signal to be periodic. From that I got, we know the value of omega naught is 2 pi f. If 2 pi cancel, f equal to k by n. So for a discrete time complex exponential signal to be periodic, it has satisfied condition omega naught by 2 pi equal to k by n or f equal to k by n. So with this explanation of these three topics. Okay, This is today's class. Next, we will go for the jet transforms. Thank you. Thank you, one and all.